let's look at TLS then, and we can go from we can build on where we left off last time. Okay. So before we get started, I think the thing that I'd like to remind you of is kind of the attacker model that we have from before, and kind of where TLS sits in, and what's the thing that we should be thinking about when we think about TLS. So if you remember from the networking attack or networking lectures, the network attacker is kind of the model that we really care about, and really kind of like this is this answer to a bunch of our networking insecurities, right? TLSs at least, right? So in this model, the attacker controls the network infrastructure. So this might be actual physical routers between you and, say, a server you're trying to talk to. It might also be a DNS server, or a DNS server that they've compromised. So kind of like they have lots of things to control, and they can do things like eavesdrop, inject packets, drop packets, modify packets, and route, so on and so forth, right? So kind of two realistic scenarios where you might have this kind of attacker is, your Wi-Fi coffee person. They're sitting at an internet cafe, really just a cafe. Every cafe is now an internet cafe. Can intercept packets, inject packets, do all these things that we talk about. You might be at a hotel. Anybody local to that network can do the same thing. You might be at UCSD. They can do this too. And honestly, like kind of anywhere within kind of these shared infrastructure networks, these kinds of attacks are pretty realistic, but they are also realistic at a bigger scale. Like if you're a nation state attacker, right, you can control DNS, you can control BGP, and these are things that we should be worried about and we'll want to try to address with TLS. Okay, so our goal is to basically establish a secure communication channel between two different hosts, typically your browser and typically a web server. And what we'd like to get is confidentiality, integrity of the messages that are being sent across these channels. And we'd like to make sure that when we talk to a web server, we're talking to the right web server, right? So this is the authentication of the remote host. And sometimes we'd like to know who the client is. So we may actually want to also authenticate the client. We typically don't do this with TLS, at least like not the way most people use it. But if you have two servers talking to each other, you can do authentication both ways. Okay, so how do we construct this secure encrypted channel? Well, at the lowest layer, right, like the thing that we build up to is we're going to use something like AES, so a symmetric primitive or symmetric block cipher with an encryption key, say KE here, that encrypts our message, and we also send over a token that's the MAC of the ciphertext C with some other key KM. So both parties have KE and KM, and kind of how do we get to that point where we have these two keys? Well, we're going to derive them from, say, our Diffie-Hellman key exchange protocol, right? So to negotiate the symmetric keys, we're going to use Diffie-Hellman, so DHE, and then we're going to essentially just Alice sends Bob GA, Bob sends back GB. They have now, since Alice has A, Bob has B, they can take whatever they receive from the other end to the power of whatever their own variables are to get GAB on both ends. In the assignment, you're just going to use this shared secret for everything. In practice, what happens is you have a key derivation function, which takes a secret like our GAB here and actually produces the keys that you care about. So usually it just produces like a bunch of random bits, and you can chunk out those bits however you want. In our case, we're going to chunk out those bits into two keys, KE and KM. So our encryption key, our MAC key, and we're going to do this on both sides. And this is how we get the two keys to encrypt and MAC. Okay, now is this actually good enough? Are we, if you remember from last time, that there's a little bit more to the protocol, right? Like this protocol is particularly busted. How is it actually busted? If you think back a bit. Suppose this was it. How is this super duper wrong? What can our network attacker do? Yeah, so they can man in the middle. I mean, they can strip the MAC, but if they strip the MAC, then you at least know that like that's an easy thing to detect, right? But they can actually carry out a man in the middle attack, right? So they somebody that intercepts GA and GB. Well, like if I'm intercepting here, I don't have to actually send Bob GA. Remember, I can send GM and I can send Alice GN, right? And then they end up computing shared secrets that the man in the middle has with them, and the man in the middle can intercept all packets thereafter because they're going to end up with the shared secrets that's common between the two parties. Do y'all kind of remember this, or do we need to actually go over this? So if I'll just bring back the quick slide from last time, because I think like if we don't remember this, we're kind of hosed. Okay, so let me bring back the last week's slides where we had Mallory in between. Right, so if you remember this slide, right, Mallory can send GM to Bob, GN to Alice. She can internally compute GBM and GAN, right? So she's going to establish a shared secret between herself and Alice and between herself and Bob, and she'll be able to encrypt and decrypt everything thereafter, right? Because this is everything that we care about depends on this shared secret. If this is compromised, we're totally done. All right. Okay. So how do we fix this? Well, the fix is authentication, like we talked about last time, right? So one way to do this is when Bob replies to Alice, he not only sends GB, but he also actually authenticates everything that has been said. And the things that have been said are these two messages here, right? So he will sign GA and GB, and he's going to sign it with this key B. So it's an RSA key. So he internally has a private RSA key B, and that's the thing that he signs the messages with. And along with that, he sends the corresponding public key RSA pub B here. Now Alice gets this key here, and can verify the signature and what has been actually sent, because she knows she sent GA, she knows she received GB, so she can actually verify like, yes, actually like the thing that was said between the two of us was GA GB. Right? Now what's the problem with this? No, right. So she sends GA, she receives GB, and Bob then says, hey, okay, the thing that has been said is GAGB, right? So she can confirm, like, yes, the thing that has been said is GAGB because she has GA, she has GB, and she gets the signature from Bob, right? So she can verify the signature using this key here, the RSA public key, right? And indeed, there's nothing like funny going on underneath the hood, right? She can take this RSA public verification key, call the verify function with GAGB, and that signature should match this thing here. Yeah, there is a problem with the public key, right? Bob is just sending the public key. So if we get the public key, why should we trust this public key, right? Like somebody in the middle could have just signed GAGB with their private key, sent us their RSA key, right? So if the way we're getting these public keys is by sending them on the wire, then somehow we need to figure out, okay, like how can we trust this thing? How do I know that this is actually Bob's key and not Mallory's key? Right? So like we need to somehow make sure that this key that we just received over the wire is actually Bob's key. Because if it's not Bob's key, then we could have just been men in the middle again. So, okay, kind of like one of the things that we have to address here is how we get, or how do we check that this is actually Bob's key? This is kind of like the goal of today's class, building on where we were last time. So how do we establish trust in these keys? Well, one way to do it is Alice and Bob met somewhere at a key signing party pre-COVID, and they shared, key fingerprints. This doesn't really work, right? This is basically as bad as trying to share secret keys offline in person, right? So we need something that actually works at the scale of the internet, and something that actually would work for your browser talking to a web server. Okay, so how do we do this? Well, one way to do it is to do this fingerprint verification. So like we're going to verify fingerprints, not the actual keys themselves, and a fingerprint is basically just a hash of the public key that we've exchanged through a separate channel. So this is called tofu, and you've all seen this already. All right, so I'm going to just show you an example of tofu by pulling up a terminal. Okay, so here I have a terminal, and I'm going to, let me first edit my SSH known hosts. Elk, let's go with elk. Okay, great. So I'm gonna SSH into one of my machines, elk.sysnet.ucsd.edu. And what's going on? Well, I'm connecting to the server, and I am getting an ECDSA key fingerprint. This is the fingerprint that the server is telling me, like, hey, this is the fingerprint of the server. Right? So what can I do? Well, I can accept it or I can not accept it. So I have, unless I've written this fingerprint down somewhere, there's no way for me to know that I'm talking to my particular server. You can actually check the fingerprint. So like, because I have access to this machine, I can actually compute this fingerprint and write it down somewhere. But basically, anytime you SSH to a machine, typically, like, none of us actually do this. We just type in yes, right? And then we're going to type in our own client. So this is my client key, which I'm going to type in 2 seconds. And voila, right? I'm now SSH into the machine. So anytime I SSH again, it just asks me for my client key. It doesn't ask me to check or trust the fingerprint of that server, right? So what happened is I go to SSH, known hosts, and if we look at the end, I have here one entry, which is for elk.sysnet.ucsd.edu. This is the IP address, and this is the actual public key of that SSH server, right? So if that first time when I said yes, that connection wasn't man in the middle, then from then on, because I've stored this public key, we're in a good situation. But if I was man in the middle, then all bets are off. Somebody could have totally man in the middle our communication. As long as they're always online, they can intercept packets. I guess with what we're actually doing here, it's a little bit harder, but with RSA, it'd be pretty easy. So let me show you what happens if you're potentially gonna get man in the middle. And I'm gonna SSH into actually my local machine, which is bushwick.programming.systems. Hopefully this will play nice. Great. Okay, so what happened? Well, I have, if we look here, Bushwick, I have an entry here for bushwick.programming.systems. This is the public key for that server. Now, what happened? Well, it turns out that whatever the server is actually announcing doesn't match what I have in my known host file, right? So like there are two things that could have possibly happened. There's a DNS spoof, and actually bushwick.programming.systems points to a different machine, so it has a different IP address, which means that that server at this different IP address is saying that it does have an SSH server. Its key is just different from the key that I have saved. The other thing is it could just be that somebody is doing something nasty and potentially man-in-the-middled our connection and is instead pretending to, again, be an SSH server. Or it could be something totally like not malicious, which is the server changed its key, which is exactly what happened here. So if we go, how do we fix this? Well, we go to entry 28, we get rid of that entry, and we now SSH this machine. It looks like it's the first time we're connecting to this thing. So again, we're going to accept this thing and then move on like we did before. So I'm not going to type in my password again. Right. So this would look like a tofu thing, but basically what I was trying to demonstrate is that you can actually catch these things, and these are pretty useful. And sometimes the tool tells you what kind of attacks you may actually be hitting. Do you have any questions so far? I think a bunch of you ran into this SSH problem in your assignments, because I think you're SSHing into the same IP address, but the key is different between the machines. So it's something to be mindful of, that if it's not a homework assignment, it's something that you do actually want to pay attention for, even though, the likelihood of an attack against you is probably pretty low. Okay, but SSH is not the only piece of software that actually uses this tofu model. We have it for many other things. If you use Signal, right, when you talk to somebody on Signal, you just start talking. You don't actually check whether or not anything has actually happened, but you could check to see or you can establish a secure channel, forever by actually performing a similar kind of check. So like the assumption, like with Signal, is pretty similar to SSH, where if the connection hasn't been man in the middle the first time you connect, it's secure from thereafter. But you can go a step further, much like we can check SSH fingerprints with the actual server fingerprint. With Signal, there is, if you pull up your Signal app, there is a way to verify the identity of the other person. So if you're near each other or you have a separate out-of-band channel that you can communicate with, you can either take photos of this QR code, or you can like read it to each other over some channel that is actually them and not somebody else man in the middle. And that like it tells you that like actually the tofu establishment that you had was actually with the right person, and it hasn't actually been man in the middle. But until you actually do this, you don't know whether or not you've been man in the middle. Do any of you use Signal? All right, there's at least 2 people. The rest of you should totally hop on it instead of other communication channels. It's built by crypto nerds. It's pretty good, and it's actually encrypted, and they have no serious kind of incentives to not have it be encrypted. And the people building it are actually legit. So WhatsApp actually uses Signal's protocol underneath the hood, but WhatsApp is built by Facebook. Not that they're deliberately going to screw it up, but trust Facebook if you want to trust Facebook. They haven't exactly been the most ethical company. If anything, they've been one of the most unethical companies. So I would just use the real deal and get your friends on it if you're concerned about them not being on it. All right. So, okay, we talked about SSH, about Signal a little bit. But how else can we establish trust and keys? Well, one way to do it is you can just hard code the public keys in software or sometimes in hardware. And this is done with certificate pinning in browsers. So your browser actually has a bunch of keys that are basically baked in. There was a way for you as the web server to essentially reply back with a header, the HPKP header, that says, hey, anytime the client talks to my server again, it should only use this key. It should never use any other key. This is now actually deprecated. It turns out that the attackers were using this to essentially get people to to take websites off the internet, because you're saying you can't talk to me with any other key from this point on. If you ever screw anything up and there's ways for attackers to get you to screw up. They can get your clients to try using that old key, which now might actually be busted, and you try to like change your key, but turns out like that's not going to work super well. So this is no longer a thing, but the thing that is a thing is your browser has a bunch of baked in keys, and that's what we use to bootstrap everything else. And we're going to talk about how that actually works in a couple of slides. In particular, this is kind of like the thing that those keys are certificate authority keys. So that's, I guess, like you could pin other kinds of keys, but really the CA ones are the ones that we really care about. And this is kind of the whole public key infrastructure that we rely on the web and kind of outside the web. Okay, so what is a CA? A CA is either a commercial or nonprofit trusted party. One example of a CA is Google. They issue certificates. And certificates are basically just fancy ways of saying keys that are signed with other keys. We'll understand what certificates are by the end of this lecture. Another nonprofit, which is kind of the thing that changed the game in the deployment of TLS and the deployment of HTTPS on the web, is Let's Encrypt. Let's Encrypt is awesome. They do this without asking you for money to pay for certificates, but until Let's Encrypt, they were very, like most companies would charge you money for issuing certificates that you can use for your websites. Okay, so certificates, their whole kind of job is to keep like one secret for real secret and kind of off the internet. And then they're going to use these certificates, these keys, to verify public keys and sign them. So basically, you can ask a certificate to sign a public key for you. They'll sign it for you if you can prove that you are the person that, for example, owns Google.com. Now, if you trust a certificate, then what happens is you end up trusting all the keys that this a CA. You trust all the keys that this CA actually signs. So kind of we build this like chain of trust that if the CA says something, they can kind of sign certificates for other CAs. So we can have kind of like a whole hierarchy of certificate authorities that we then use to kind of at the leaf sign keys for our web servers. But web servers aren't the only thing. Right? Like you can also use this to sign software. And for example, like this is what Microsoft does. They signed a software with a key that has actually been signed by a CA, and then you can verify that it was actually a legit update from Microsoft when you get this particular update. But that's not the only way we can assign software. Like one other popular way is to use PGP. And PGP is kind of an implementation of the idea of the web of trust. So unlike the CA model, where we have, say, a select few CAs that we trust, in the web of trust model, you kind of decide yourself who these trusted parties actually are. And then you can transitively, again, trust the keys that they sign. So for example, here I have an example of editing a key for Ron Rivest at MIT, and with GPG, you can kind of select how much you trust Ron, and if you trust Ron ultimately, then you'll trust whatever Ron actually signs with his personal key. But this is not the only thing we can do. We can also say, this is, for example, my key. So one thing I can do is with my key sign, say, my GitHub commits, so that you can check that the person who actually put this code in this repo is actually me, right? So like if there was a backdoor that I inserted, you can then go back and blame it on me. Let's see, GPG list keys. So what I use GPG for largely, and I don't really use it seriously, at least not anymore. I largely use it to, for example, get my Tor browser. So Tor is a browser. It's a privacy centric browser. So whenever they actually release new versions of Tor, they sign it with their keys. I have their key in my key store here, and I can use the public key here to actually verify whatever binaries they may actually send. But you can also use PGP to encrypt email and things like that. We don't for real, because it's kind of crap at the end of the day. That's the single word description what I would say PGP for email actually is. We're just like really bad at it. So I think there's no point in actually even trying. If you're trying to do secure communication, you should probably use Signal. Keybase is kind of like a nicer version around PGP that addressed a bunch of the usability problems in PGP. But that the company that built Keybase is owned by Zoom, and who knows what's actually going to happen with the Keybase servers. But it was a really nice way of trying to make PGP usable. Okay, so back to our communication diagram, right? So okay, like how do we actually trust the RSA public keys coming from Bob when we get it at this point here? Well, we're going to use one of the methods that we talked about. In particular, we're going to use certificate authorities. But that's not the only thing that we have to be worried about. We have to make sure that somebody that's intercepted our communication channel can't replay messages, right? So like we want to make sure that if somebody is like intercepts any of these things, they can potentially later use these messages or just play them back to actually create a man-in-the-middle channel. So we want to make sure that you can't ever send a message and make it look like it's a new message. So the way we're going to do that is by using nonces. So instead of just sending our GA, we're going to also send a client secret to RA. And when the server replies, or when Bob replies, Bob is going to reply not just with GB, but also RB. And importantly, when we actually sign the message transcript, it will include not only GA and GB, but also GA, GB, RA, RB. Right? So it's going to include everything that has actually been sent. And this prevents basically these class of replay attacks. So this is kind of what TLS looks like, but it's just a little bit more complicated. But at a high level, this is basically what's going on. So we send a bunch of random things, the GA parameter, send GB, then we sign this thing. We're going to verify the public key, verify the signature once we've verified the public key, and then we're going to have an encryption key and a MAC key that we're going to use for sending HTTP traffic across the wire. So RA and RB are just random, like they're just random nonces. So they're like random bits. They don't have to. There's nothing special to them. We will actually for real use them in our key derivation function, but they're just random bits. And the reason we have them is to make sure that you can't make it seem like an old key establishment is new, because you can't just play back GA. You have to play back GA and some random thing, and we're never going to reuse the same randomness. Okay, so let's see. So couldn't the adversary also get RA and RB? They totally can. So they can get RA, RB. They can also get GA, GB. The important bit is you can't take an old message and replay it, right? So like if I've recorded a bunch of communications and I want to take a packet that was sent from, say, Alice to Bob and make it seem like a new packet in our new channel where we have a different RA and RB, that will actually be impossible. Whereas if we just use GAGB, there is no way for us to know if this thing is old or new. Okay. So what does it mean to MAC data again? That is a great question for somebody else to answer while I have a sip of water. It's also a really good final question. Anybody want to take it? What does it mean to MAC data again? A mix of answers. Okay, so it is like a signature, but it's a symmetric key signature if we want to think of it that way. It's a magic hash that takes a secret key and ensures the integrity of the ciphertext. So what a bunch of you said is right. So like when we MAC the ciphertext, right, on the receiving end, let me erase this. So when I get a message like this, I get C and I get T, where T is the MAC of C. Then I, as Bob, can detect whether or not C has been altered by a man-in-the-middle attacker, because taking the MAC of whatever that C prime may be won't actually match the token that was sent or the digest that was sent, right? Or the authentication code. We're going to use those interchangeably. So it's basically impossible to compute one of these tokens without having the secret key KM. So as long as KM is secret, only Alice and Bob can MAC messages that they'll agree on. Okay, so kind of that's TLS, but in a super high level. We're going to look at TLS a little bit more closely in just a few slides. But before we do, I think it's worth kind of talking a little bit of history, right? So TLS gives us an encrypted and authenticated channel for sending data across sockets. So it used to be called SSL, or the secure socket layer, and you'll still hear people say SSL, and when they say SSL, they typically mean TLS, not actually SSL, because SSL was terribly insecure. So SSL 1.0 was actually never released. It was that bad. Then 2.0 was released in 95. Super insecure. SSL 3.0, insecure since 2014. TLS 1.0, deprecated, removed from major browsers. You might still see websites actually serving things over TLS 1.0, but there's like many issues with TLS 1.0. You should definitely not use it. Same goes with TLS 1.1. So there are still some sites that actually serve things over TLS 1.1. Let me see if I can find, but one of the, I think in RIA sites is served over. Okay, they fixed it. So there used to be some sites, at least like one of my colleagues' sites, that was served over TLS 1.1. And the issue is when you say like, okay, yes, like let's accept this anyway, your browser, or at least Firefox, remembers that for every site. So then any site that might be served over 1.1, it won't give you a warning about it. And that's kind of, in my opinion, a little bit of a bad decision, because you might have just wanted to opt out of one site, but you're forever with other sites, and that leaves you open to all kinds of serious attacks. Okay, so what do we actually have that's pretty reasonable? Well, TLS 1.2, and this is basically like when we say TLS, usually we mean 1.2. When we say SSL, we usually mean TLS 1.2. It's released in 08. It's not bad. There are a bunch of problems with it. So like there have been actual attacks against TLS 1.2, and we'll talk about some of them. But it's actually like a pretty reasonable protocol when using good parameters. And we'll see like what bad parameters actually are. TLS 1.3 is more recent, and it's the latest in the TLS series. It was standardized in 2018. It was actually work with a bunch of academics and industry. There are a bunch of really nice changes from 1.2, but that also means that, you know, it's not actually completely out there. So like a bunch of sites will serve things with TLS 1.3 and 1.2. I would always try to opt in for 1.3 whenever I can. But this is roughly 30% of the web, just looking at some Cloudflare data recently. So this is still kind of like rolling out, and we'll see like why it's taking a little bit. But anyway, like it addresses a bunch of the problems in 1.2, and especially the kind of the ease to screw up 1.2 has been kind of eliminated in 1.3 by construction. Okay, so what we're going to look at in the rest of the class is TLS 1.2. We're not going to look at 1.3. I suggest you Google it. There are a bunch of really nice diagrams for actually going through the whole handshake and record layer of TLS 1.3. So here what we're going to do is look at 1.2, and we're going to start with 1.2 with Diffie-Hellman key exchange. There's also TLS 1.2 with RSA. So how does this work? what we're going to look at when your browser makes a connection to a server. So you make a connection to the server, and the first thing that you do as a client is you send a hello message. So you send a client hello, which will just be a message that contains a random string and then a list of cipher suites that you support, right? So like basically your client, your browser is able to do certain kind of crypto, and you're telling the server, hey, this is the kind of crypto that I can do, right? So like what are these cipher suites? Well, you can say something like TLS, ECDHE, RSA with AES 128, GCM SHA-256. What the hell does this mean? Well, it means that what you can do is elliptic curve Diffie-Hellman for key exchange. That's what the ECDHE is. Then we can use RSA signatures, right? So that's the thing that the server should present you an RSA signature for the message that we looked at, or the whole to say that, hey, I am actually Google, and I just shared with you GA and saw GB, and I saw GA, and here's my randomness, and I saw this randomness from you. Okay, so this is for like the handshake bit. What do we do after? Well, what we're going to do is we're going to use AES for symmetric key encryption, and we're going to use AES with 128 bits. The mode that we're going to run AES in, remember, we have different modes to run block ciphers because we're going to encrypt a lot of gigantic messages. So we're going to use GCM. So AES in GCM actually does not only encryption, but it does encryption and authentication. So this is one of those authenticated and encryption mode operations. And a hash function that we're going to use is SHA-256. Okay, so kind of like this is pretty reasonable, right? So we're going to use ECDH. We're going to use RSA signatures, AES, and GCM mode with a reasonable key size and a reasonable hash function. Okay, but this is not the only thing that you can use TLS 1.2, and you can have different kinds of options. So for example, instead of this one, we can have this one or this one, right? So this version here is Diffie-Hellman. So it's not elliptic curve, it's just a classical Diffie-Hellman exchange. We're going to have RSA. We're going to use DES instead of AES. We're going to use CBC mode, and we're going to use SHA-1. Right, so there's so many things that are wrong with this, right? So like DES is no longer actually secure. It's a 56-bit cipher. CBC mode, like we spoke last time, has some padding oracle attacks against it, and SHA-1 has also been deprecated, right? But this is a pretty okay thing for you to use, right? Or it's not an okay, sorry. It's a thing that you're allowed to use. It's not an okay thing to use. And you can go like even a step further. You can just configure your TLS cipher suite to be TLS null with null null. What do you think that does? Yeah, it encrypts nothing. It authenticates nothing. It's the null cipher suite. It's the best we can do. Right. So like there is an option for you to not actually encrypt and authenticate anything, right? Which is kind of ridiculous that we're negotiating the cipher suites that we're going to talk, and one of the things, one of the options is like, well, you don't authenticate and encrypt anything. Yeah, that's a really good question. Like, when is that used, and why is this even a thing? Well, we're gonna get to that question. That's a really good question at the end. But the short of it is, sometimes governments have things to say, and they get to say things about what you as the software developer are actually allowed to include in your software, crypto wise at least. Okay, so I just want to, I guess, like, again, point out TLS 1.2, many secure options. As a sysadmin, like actually configuring this thing is error prone. People have screwed it up many times. There are websites dedicated to checking your SSL certificates. I think it's like sslfail.com. or sslfail.org, maybe one or the other. But anyway, there are sites that are willing to actually check your server configurations because we've done this so poorly. And like you might think that you're choosing something reasonable because you're not actually choosing the null protocol, but there are protocol errors around this. And there's also like a bunch of attacks where when you negotiate what encryption and authentication scheme to use, um, there are ways for attackers to get you to negotiate for the wrong thing or renegotiate later. So like one of the things that we're not going to talk about is that you can renegotiate what crypto you want to use, like midway through your your session. Okay, but for now we're going to assume that we've configured this right. Okay, so we're going to tell the server we have these list of cipher suites that we want to use. This server replies back with a server hello, which contains the server randomness. So this is the random nonce, and the cipher suite that Alice and the server are going to use. So this is step 2, the server hello, and then the server sends the public key RSA key and any CA signatures corresponding that are essentially signing this RSA public key. This is what we call the certificate. So like when the server responds, it responds with the randomness with a certificate and a proof that, hey, some certificate authority says that this is actually the server that you're talking to. So in this case, the server that we're talking to happens to be the NSA web server. Okay. Now, what are these certificates and how do certificates authorities actually work? So let's actually dig a little bit into this, right? So like these public keys, this is like ultimately what we care about. They're encoded in certificates, or certificates contain these keys and a bunch of other metadata. These certificates are signed by a CA, and the browser that you have, whether it's Firefox, Chrome, or Safari, they have a bunch of certificates for CAs that are baked into the browser, and these are considered trusted CAs. And then when you get one of these public keys, so when we get this particular message, we're going to check that this actually is a valid certificate. And the way we're going to do that is by looking at these CA signatures and the built-in certificates that the browser has to essentially check that, hey, this thing was actually signed by somebody we trust, which might be, a third level down in the CA hierarchy. So it might not be directly a CA that's baked into our browser. It might be a CA that is an intermediary, but that CA's certificate is also included in this payload. And then we can verify that that CA's key was actually signed by a CA we trust. Okay. And kind of like this is like where the idea of chaining comes into to play, right? Because we don't always necessarily get it signed by one of these root or top level CAs that are baked into the browser. And the thing that I want to point out is that certificates typically are valid for 3 months to a bunch of years. The CA keys or the CA certificates are actually like super long lasting, like on the order of 10 years. But your typical home server public key or your certificate expires after just a few months. Okay, so let's actually draw out, are there fake CAs? There are all kinds of interesting bits about CAs. So you can set up your own CA actually. So you have all the tools that you need to actually do this. The thing is, nobody's going to trust your CA. So yes, there are millions of fake CAs. You are possibly one of them. But we don't necessarily trust our CA. So if you've ever visited a website that tells you like, hey, accept the risk, and then you have to go through like that like scary login, it's possible that web server showed you a key that has been signed by that server itself and not by some intermediary that is on this chain to a root CA. Right? So you can sign your own certificates. These are called self-signed certificates, but nobody's going to trust them. You have to go through like one of these explicit warning messages that we're willing to look at your thing. We're willing to trust this channel. Okay, so I want to actually draw out what this scenario looks like, just so that we have like a rough idea um, of what each party actually contains. You will actually be implementing a server and a client, but not the CA. And I want to just briefly show you what all these bits actually are. So give me 2 seconds. All right. So I'm going to fade myself out just to make my life a little bit easier. And what I'm going to do is draw out the 3 different parties, starting with the left, which is our Alice. So we have Alice here, and Alice has a browser. And then we have our server. Let's call it Bob. And then, give me 1 second. We have, say, 1 CA. So I'm going to pretend that there's only 1 CA that we actually are going to deal with for now, but there could be an intermediate ones in between. So we have CA here. This CA internally has its own secret key. So it has some, like, let's say, RSA private key. We're going to call this SKCA. And because this is an awesome CA and it's a root CA, your browser actually has the corresponding public key baked in, right? So this is our browser. And what we have in our browser is the corresponding PKCA. Okay, so this is, let's say, the corresponding public RSA key. Okay, then how does Bob, let's say, as a owner of NSA.gov, actually get a certificate to present to the server when Alice makes to the browser when Alice makes a request, right? So like when Alice makes a request, she says hello, and in the hello or thereafter, what we're going to do is we're going to actually send Bob's public key, PK, and some signature that, Bob is actually Bob, or Bob owns NSA.gov, and that's going to be something signed by DCA, right? So what we're actually going to present is this, and then CA signature, which is essentially a signing of SKCA that Bob is right. You can think of it something like that, right? So it's the signature from the CA saying like Bob actually owns public key PK, which means that internally Bob actually has this public key. So indeed, before this communication between Alice could have even happened, Bob, to start up his server, actually generated a public secret key pair, and then got a certificate from the certificate authority, where Bob was basically saying like, hey, here is my public key, and here's proof that I am Bob, right? Or in other words, I own NSA.gov, right? And then internally, what the CA does is it takes this PK and the proof, and if it can actually verify that Bob owns NSA.gov, it then actually produces a certificate that is basically saying like Bob is, or PK is Bob. Let me be consistent here. PK is Bob, and signs this thing again with its SKCA, right? So this is the same thing as that, right? Now, how do we actually? So Bob never actually gives SK to anybody, right? So this is actually important. So whenever somebody offers to generate SSL keys for you and requires your secret key, you shouldn't do it because that's not necessary. So Bob only sends PK and a proof that he's Bob. So how did the CA get the corresponding SK for Bob? It didn't. The CA doesn't actually have the corresponding SK. So this is the, let me, maybe it's easier for me to try to color things differently. So I'm going to color Bob in red just so I don't. Okay, so Bob has PK and SK. So Bob here sends PK and a signature that PK is Bob. So PK is sent over the wire to the certificate authority. The certificate authority takes the PK and the proof. If it verifies that that is actually Bob, then it sends a certificate back that says PK is Bob, and it signs it with the certificate authorities key. Great. Before we talk about the proof, are we on the same page here? Okay, great. So internally, when Bob gets this thing, before like we actually make a connection with Alice, Bob internally also, because this is a root CA, Bob also has PK CA internally and can verify yeah, actually the certificate I got from the certificate authority is legit. It's not like something signed by some man in the middle party, right? So you can actually, again, the same thing, your browser has a baked in certificate, your OS does this too, and a bunch of times it's actually the same certificates, these root CA certificates. Okay, so kind of we talked about two things. I just want to briefly summarize. A is how Alice talks to a server and how the server presents a key, and how that key was originally signed by a certificate authority saying that that is actually Bob who we talked to. This is kind of how we get the chain of trust, right? Because we get something from the certificate authority. That's the thing that we actually trust when we get the message from Bob. And you can imagine, there are a bunch of other parties, other certificate authorities that sign the keys of this particular certificate authority if it's not a root CA. Okay, now let's talk about how do we actually prove to this certificate authority that I am actually Bob, right? So how do you prove ownership of, let's say, a domain name? How do you think? Save a page from the domain, buy the domain name from the person offering CA. I don't know what to buy the domain name. You still have to prove. So it could be that the CA is the one selling these things. So the domain names are registered how? So okay, there are a bunch of different ways. It depends on the certificate authority and how they choose to do this. So for example, when I got these wildcard certificates a while back, I had to present my passport. So for certain, at least at the time for those domains, you have to present a passport and you have to say that you own this particular domain. The way you prove that you own that domain is one in several ways. So this was Start SSL's approach, was you have to be able to respond to an email from postmaster at your domain.com, or you have to put a file up containing these random contents at this particular URL of your particular website. What we really do now, or at least what Let's Encrypt protocol, which is the Acme protocol, does is one of the ways. There's multiple ways, but the one that I use, and maybe if we have time, I can show you. Actually, you know what? Why don't I just show you 2 seconds? Terminal. Nope, not MVM. 1 second. There we go. Okay. So let me fade to this. And all right, I'm back. Great. So I'm going to SSH into my DNS server. Great. I'm in this DNS server. I'm going to. Okay, well, that didn't work. cd etc bind 9. This is where my DNS server stuff actually is. So I'm going to edit db.programming.systems. Now, if you'll remember, I had this Acme challenge here when I think showed you this DNS thing before. But the basic idea is the CA can ask you to add new entries to your DNS server. In this case, it says like, hey, please add a new DNS entry for Acme challenge.programming.systems. And it will give me some random thing to put in here. And then I update my DNS server. Then what the CA does is it performs a DNS query to this name server and says, hey, is the thing that I told you to put there actually there? And here is how I would, for example, do it on this particular machine. I kind of have it in my history. Let me, well, my screen is totally busted here. Term. Let's try this. Well, okay, maybe not. It doesn't matter too much. Basically, I make a request to this web server, which is https acme version 2.0 at let'sencrypt.org. So Let's Encrypt is one of the CAs. It's a root CA. And I say like, hey, the thing that I want to get a certificate for is programming.systems. Before this D, there was star.programming.systems. And then what the thing basically says, like, okay, here is a DNS entry that you need to add to your table, and then I'll make a query, and you do this 2 times, and if it finds the thing there, then you're good to go. Okay, so let's actually take a look at what these certificates look like. So I have a bunch of slides here, but I thought it's actually nicer to just pull up an actual certificate and take a look. So let's do that. All right. So here I have the TLS spec. Okay, so I pulled up a few certificates. There are easy ways for you to do this. I'm going to show you very quickly in Firefox. If you click on this thing here, connection secure, it says it was verified by Internet 2. If you click on more information, it'll pull up this dialog, and from that dialog, you can go into viewing certificates. But anyway, this is one way to look at that certificate. So what does it actually contain? Well, it contains a bunch of information about who issues this certificate, right? So who is this actually for? So this is the subject name, and the common name is the thing that we really care about, which is csc.ucsd.edu. Then we have a bunch of information about who we're actually trusting, right? So who actually is the entity that issued the certificate. In this case, it's Internet 2, and it's the organization will use it in common. This is their common name, in common RSA server CA. So this is an intermediate certificate authority that generated that signed the UCSD or the csc.ucsd.edu public key. Now, what else does this thing actually have? Well, it has like information about how when can you start using this certificate and when should you stop using it. So if it's outside of the state range, you shouldn't trust the certificate. That's what it's telling the browser. So the browser has to actually check this. So the client, when he gets one of these certificates, it should make sure that actually the current date is within this range. The other thing that it says is, well, okay, I'm going to ask for a certificate for this common name, but I can say like, actually, I'd like a bunch more other domains to use the same certificate for, and this includes csc.ucsd.edu, cs.ucsd.edu, www.cs, blah, blah, blah. So all these things here, right? Then we get to the interesting bit, which is like, let's get our information about the actual key itself that in common actually signed. So the key that we have or that we presented is an RSA key. The key length is 2048 bits. The exponent is 65537. Right? So this is like one of the 2 exponents that we use. We don't typically use 3, but there were keys that used to do that. And here's our RSA modulus, right? So this is our N. So this is P times Q. So whatever that is, P times Q, we don't know what P and Q are because we can't factor this modulus. Then we have a bunch of other information like what the actual fingerprint of this thing is, and kind of a little bit more information about the entity. So it says that this is not actually a certificate for certificate authority. And the purpose that we're going to use this for is digital signatures and encrypting keys. And we're going to use it for authentication, not really for client authentication. So server authentication for real. There's a bunch of other interesting information like the CRL endpoint. So CRL stands for common revocation list. So this is like if the key gets revoked, which we'll talk about in 2 seconds, this is where you can go find that information. And then a bunch of other information about OCSVs, also about revocation. So that's like another way to get a bunch of that data. Now you'll notice that this is an intermediate CA. So we're also going to have a certificate for the key, the public key that corresponds to the secret key of this CA that signed the UCSD certificate, right? So here we actually are just going to bundle the certificate authority's public key, and this thing was also has its own key information. So this has the same exponent, has a different modulus, hopefully, and it has a bunch of information like this is actually used for the certificate authority. And let's see, who was it issued by? It was issued by the user trust network. Great. Okay, so this is its common name. Now we can look at that. This is also the certificate for this particular CA. We'll notice it's a CA, but this thing was actually not issued by anybody. It was issued by itself. Right? So this is a self-signed certificate. It's one of those things. But the difference from the other certificate is that if we look in my browser, so if you go to About Certificate, we should see that particular CA here. So we're looking for User Trust Network. So if we look for User Trust Network, aha, here it is. This is baked into my browser. Right? So this is kind of like, if we look at the chain, UCSD says like, hey, this thing signed my certificate. This thing says like, this thing signed my certificate. This thing is in my browser. Therefore, I trust the certificate that comes from csc.ucsd.edu. Okay. So I know I said quite a few things, but basically you get a bunch of keys, and you can look at these keys. So what we can export we can download the actual certificate, and I'm going to show you how to look at them here. So here I have a bunch of certificates. One is for CSE, ucsd.edu chain, then ucsd.edu and programming.systems. So if we look at OpenSSL, let's do this one. So what this ends up doing is, okay, let me actually show you what this thing actually looks like first. ucsd.edu.pem. So this is just a certificate. It's encoded in this special format. When we decode it, and we decode it by passing it to the OpenSSL command line tool, then you can use that to actually parse those encoded bytes to get essentially the same information that the browser presented, slightly slightly better, I guess, is one way to look at it. So we can have like the same information that we did before, and a bunch of kind of the other bits that we saw prettied up in tables. Okay, the last bit that I want to show you is a slightly different key, which is the key for wildcard.programming.system. So this is my key. This is the modulus for this key. The bit that I want to highlight is at the end, we have this embedded SCT, which stands for Signed Certificate Transparency. And this is basically telling you like, hey, like if you want to figure out, like that this key was actually, when was it created and who actually like signed it, you can go look it up according to this globally numeric log ID. So there are people who actually check all the keys that have ever been created to deal with a bunch of attacks that we've had on CAs. Okay, but before we talk about those, I want to talk briefly about this revocation thing. So what's the point of revocation? Well, keys get compromised, right? And if an attacker can get your key, they can now impersonate you or read messages that were meant for you. You can set those expiration dates, which is useful, and that's why we have short expiration dates. But this is also why we have kind of a revocation protocol built in. So the idea between of revocation is you're basically saying publicly like, hey, my key was compromised. Please don't use it henceforth. Or like, I lost my key. Please don't use it anymore. Don't trust anything that I might sign with this key. Right? How does this actually work? Well, when you generate your key, you actually generate a revocation message essentially that says like, hey, like, don't trust this key anymore, and you sign it with the key that you generated, right? So somebody else can actually verify that you're the one that actually signed and said, please ignore my key. Now, the important bit is that you should hide this revocation message in a secret place, but not too secret where you can't find it, so that you can later actually make it public. Because like, if you actually lose your key, then there's no way for anybody to say like, yeah, well, you've lost your key, so how like, there's no way for us to trust that it's not just some random person on the internet saying, I lost my key, please stop trusting me. This is why we create these revocation messages. Okay, but certificate authorities can also revoke keys, and this is like why we have these things at the end of the certificates that say like, hey, please check over here to see if this thing has been revoked or not. Okay, so what are your root CAs? So we kind of like saw a few examples. If you pull up your Mac thing in your I forget the name, the keychains program, you should see a bunch of root CAs. You already saw what it looks like in Firefox, where you go to About Certificates. But your browser, your OS has these too. So if we go back to my machine here, if I go to Etsy SSL, there should be a bunch of keys here. So if we go to certs, there are a bunch of certs here, and these are my root certificates. Maybe that's an ugly way to put it. So here are a bunch of certificates that I trust, and probably one of them is the one that we saw earlier, which is user. Okay, maybe I don't have it here, but anyway, these are essentially the root CA keys in your OS, and programs like curl, for example, use these things. So if we do curl-v, say https programming.systems, we're going to actually see a few interesting bits here, which is before we actually do HTTP, we're going to actually do the TLS handshake. So client hello, server hello. We do the actual encryption extensions, certificates. We get the certificate. We verify the certificate. Handshake is done. Where do we actually look for the CA key? Well, it's in Etsy SSL certs CA certificates .crt. So CRT is the name for the extension for certificates. Then we actually can finally establish our actual secure channel, which is AES with 256 GCM and SHA-384, and we're going to use TLS 1.3 instead of 1.2, but you kind of get the gist of it, and everything from then on is actually encrypted. Okay, now I have two questions for you. Which CA can issue a certificate for FBI.gov or NSA.gov, and which CA certificate can issue certificate for Google.gov if you're just kind of squinting at the list that I have on the slide here? What do you think? So who can issue certificates for FBI.gov? The Federal Common Policy, Federal for FBI, Government Root. The answer is everybody. Right? So like a CA can sign a certificate for whatever domain. There's nothing that makes one CA more special than the other. Now, of course, the FBI might want to just get a particular CA to sign their public key, but anybody can actually sign a certificate for FBI.gov. Yeah, so GoDaddy can sign for the Gov. I mean, maybe there's some weird regulation, but there can't be, because that would be like super weird kind of exclusion. So this is kind of scary, right? I think exactly what you're kind of getting at. GoDaddy, which seems like not necessarily the greatest company, or maybe it's okay. I don't know. Like whatever. Their site just kind of like is a little silly. But there have been like historical cases of CAs being malicious or getting owned, and the attackers taking advantage of the fact that they owned a certificate authority um, to issue certificates for websites they shouldn't. So for example, Komodo and DigiNotar, they got hacked in 2011, and then they actually issued certificates for Gmail and things like that. And it turns out that these certificates were actually used for man-in-the-middle attacks in Iran, right? So that's super duper scary. So as a result of that, there is the browser has basically said no, thank you. And there's an advisory that, for example, Mozilla had that basically, and both Mozilla and Chrome were like, we are done, and we are removing DigiNotar from our browser, right? So the browsers actually have a lot of power. They're like, you screwed up so bad, you're done. Guess what happened? DigiNotar went totally under, right? So like, if your whole business model is to be a certificate authority, you have one thing to do, which is don't get hacked and don't be evil. They kind of screwed this up. So there were evil ones too, like Turk Trust issued fraudulent certificates for Gmail. An Indian certificate authority issued certificates for Google and Yahoo. WoSign in 2016 issued certificates for GitHub, so on and so forth. So Cameron had a question. Can I say again how each certificate in the chain can prove that another one signed it? Yeah, so I'm just going to go back to this thing here, right? So here I have ucsd.edu. This is one certificate. This certificate was signed by Internet2. Okay, so the common name for that is in common RSA server CA. Yeah. This is not root CA. So if we look at the root CAs, in common, you're just not going to find here. Okay. But we still, somehow this worked out. We're able to make a connection to ucsd.edu, and it's totally secure. I guess you can't actually see what I'm clicking on, but the little button here is locked, not unlocked. Okay, so how do we know that this is okay? Well, what we're going to look at is this thing. We're going to look at the public key for this CA certificate. We have that here. So you basically get, when UCSD replies, they don't just send you their certificate, but they also send you the certificate from that CA. In this case, the in common RSA server certificate. This certificate says like, hey, this is my public key, and it was signed by the user trust network. Okay. Now the user trust network is actually a root CA. So we just looked that up in our browser. Check that this certificate has been signed for real by user trust RSA. And then we check that this certificate, the UCSD one, was signed by the in common RSA server public key. Did I answer your question? Okay, great. Okay, so and like I'm glad you brought this up, right? So like there's going to be intermediaries, and this is kind of going away a little bit with Let's Encrypt, because Let's Encrypt is a root CA. They can sign things for us. But sometimes we do have like quite a long chain, and not everybody in that chain is necessarily doing so well, right? Like this is a hard job, and it's really easy to screw up. So unsurprisingly, we're going to have people getting hacked. We're going to have people doing malicious things, and somebody's got to like keep this in check. So one way to try to deal with this is certificate pinning, and this is kind of the HPKP thing that is actually deprecated, which is we're just going to bake in some certificates for some sites. So for example, I think Chrome bakes into certificates for Google domains. But I could be wrong, but I'm pretty sure they do that. It used to be that you can also say like, please only use this certificate from this point on. We don't really do this. What we really do is we use certificate transparency. So basically, when a certificate authority actually issues a certificate for a particular domain, they actually publish on an append-only log, like a global log, the certificate that they issued, and then other players check this log and the certificates that you've issued. So this is kind of going back to the to the certificate that I have, right? The programming.systems one. This is basically like a thing that Let's Encrypt published to. So like if you go look up the Komodo or the Google Xenon 2020 log, you should be able to find that, Let's Encrypt issued a certificate for programming.systems on this particular day for this particular key, right? And as long as we all kind of check and everybody like basically like if you want to play ball, if you want the browsers to include you here, you essentially have to play ball here. We can actually keep track of certificates that are issued by different players, and over time, like if people screw up, we can boot them off of the list. And like Symantec essentially did this a few times, so I think they've also been completely removed by now. Okay, so I still have quite a few slides to go over. Let me see how many, but you know what? There are enough slides that I think we'll just continue next time. So I'm happy to stick around for some questions, but I think next time we're going to just continue with TLS and maybe also get some hands on a little bit of experience writing a little bit of code with the DSL that you'll be using for the homework. But I can stick around for any questions, and we'll leave off next time. Have root servers ever been hacked? So what you're seeing here is a root server that has been hacked. So DigiNotar was, I forget, what was it? Is it a Dutch? I think it might have been a Dutch. No, yeah, it is. Yeah, so it's a Dutch. It was a Dutch CA. They got hacked. The hackers issued these certificates. These certificates were actually used to man in the middle people in Iran. And like when this was notified, the Dutch government actually took over the DigiNotar, but the browsers also removed it. And in fact, like if you look in your browser, you'll actually see. Actually, you should see it here. So going to About Certificates, if we go to Servers, we're going to see DigiNotar here, which is basically saying like, hey, don't trust anything coming from this root CA. This is a really awkward interface. We should probably like make it slightly better because it's not super clear that this is what this is saying, but this is basically saying like, this is the root CA certificate, and that's the one we should not trust because that one has been actually used maliciously. Okay. Okay, so let's end the lecture bit, and well, let's not. There are some questions. Shane, do you mind actually putting that in Piazza, not here, so that we can keep the lectures contained? Okay, so Cameron, how come names of TLS and SSL are so different if they serve the same function? So it started with the name being SSL. So if we go back to here, it started with the name SSL, and it was still called SSL up until 3.0. But from then on, just to kind of wash off the dirtiness that was the insecurity of SSL, we started calling it TLS for Transport Layer Security instead of Secure Socket Layer, because it's meant to be a transport layer thing. And in fact, with TLS 1.3, one of the really fun bits beyond security is that you can take advantage of faster handshakes by actually like tying in with TCP. But yeah, there's anybody that really says SSL nowadays, unless they're talking about the ancient ones explicitly, they usually actually mean to say TLS. So I don't think anybody would seriously mean SSL 1.0 when they just talk about SSL, unless the context is talking about old brittle things. It's an unfortunate naming, but it's kind of like what we're stuck with. How does group messaging work with all of this? What do you mean? What kind of group messaging? We talked about nothing messaging. So messaging things are like very different. So like what Signal uses for a protocol is different from the protocol that we're actually talking about here. So like you'll see how TLS works in more full. I think you kind of hopefully have a rough gist just from kind of this thing here of kind of the beginning parts of TLS. But messaging systems have a whole other thing because we don't have a CA to like tell us like, hey, this is actually, Bob's key. And groups make it even more even trickier. We can totally talk about that. I guess, like, if you want next time, we should have enough time. But um, I'm kind of weary of saying things about group messaging because those protocols are themselves like full lectures. Why isn't certificate privilege pinning more common? It seems like a good way to set up privilege separations for different CAs. Um, so I don't completely understand the privilege separation bit. Maybe you can clarify that. But like, one of the reasons we don't really do certificate pinning, and I guess you can, what we mean by certificate pinning is it can be tricky. So like, your root CA certificates are kind of pinned, but if you want to pin server certificates, the reason we typically don't do this is because suppose you actually screw up or want to update your certificate, whatever the reason may be, you've just announced to, like, let's say, a million of your clients that they should never talk to you on any on a channel that's signed with a different key, right? So like, any other time, like, you try to present a different key, they should not talk to you. So what this basically means, if you totally screwed up or lost your key or whatever the reason may be, you just lost a bunch of clients. So it turns out that this is actually a practical problem. Like, at a high level, this seems like a great idea, right? Like, I saw your key, I'm gonna just use that key forever on, so pin it. In practice, it turns out we're really bad at this, and attackers can take advantage of that. Yeah. All right. I will let you all take off. Thank you, and I'll see you on Wednesday.